Our next set of speakers here from NTT Communications. They'll be speaking today on the potential for attacks leveraging GitHub Actions. And the title of their talk is The Dark Playground of CICD Attack Delivery by GitHub Actions. Please welcome Yusuke and Kiyohito.
Thank you for the introduction. Hello everyone. Today we talk about techniques related to GitHub Action. So our main topic is CICD security. So I hope it will be useful and exciting for cloud operation community. First, let me tell you about us. I'm Yusuke and he is Kiyohito. We are from Japan and work for NTT Communications, Japanese telecommunication company. We work as offensive security researcher and sometimes work as internal red team. This is our presentation agenda. Our talk goes like this. First, we talk about basics of GitHub Actions. GitHub Action is a CICD platform provided by GitHub that allows us to automate, build, test, and deployment pipeline. And this is a component of GitHub Action. There are some terms, events, runner, job, and action. In our presentation, runner and action are important, so I will explain a little more detail. There are two types of runner, GitHub hosted runner and self-hosted runner. In short, the difference is the resource owner. GitHub hosted runner run with resource provided by GitHub, and self-hosted runner run with resources provided by user. Runner supports some of operating system, macOS, Linux, Windows, but our research focused on Windows. Next, let's look at custom actions. Actions are individual tasks in the workflow. We can use a combination of actions to suit our purpose. And we can also create and publish on actions in the GitHub marketplace. There are different types of custom actions. Three types are available, but we have targeted JavaScript action and composite action that support Windows. So much for the basics and deep dive into the main contents. At the beginning of the research, we analyze the behavior of JavaScript action. The figure is visualized process behavior. As you can see, runner.worker.exe executes node.exe and gives index.js as argument. This index.js is defined as entry point in the action metadata file. And the script engine node.exe is included in the runner application package. Observing this behavior and specification, we produce new attack techniques. What do you think of when you hear the JavaScript? In general, it is the script language, the core technology of the World Wide Web. On the other hand, some may think of JavaScript, implemented by Microsoft. There is basic compatibility, but JavaScript and JavaScript are different. Our research focused on both JavaScript and JavaScript. I mean, we considered two techniques for each. First, we introduced the JavaScript version. We call this technique malicious JavaScript custom action. This is a technique for executing JavaScript from JavaScript custom action via binary hijacking and masquerading. Here is an overview of this technique. For the attacker prepare workflow and custom action like this. The workflow had two steps. First step, replace the binary, and second step, execute the custom action. This custom action is implemented in JavaScript, not JavaScript. The behavior of the endpoints when the workflow is executed is shown in the right figure. Copy wscript.exe to node.exe and index.js is executed from node.exe. We hereby add composite action. This one allows us to bundle multiple steps into one action. The figure on this slide shows how it changes with and without composite action. With composite action case, the workflow is consolidated into a single step. And these two steps are defined in the composite action. I'll explain later why we combine composite action. Finally, the JavaScript custom action combined with the composite action look like this. We call this technique as malicious JavaScript composite action. And here is the actual POC code we developed. The workflow calls composite action. Composite action copies wscript.exe in step 1 and calls the custom action in step 2. Then index.js is executed from the custom action. Index.js is written in JavaScript in which the attack is implemented. Attacker can arbitrarily attack by changing the JavaScript implementation. So I have a quick demo of infecting Cobalt C2 from this technique. Let me show you. The left side is the attacker's point of view and right side is the victim's point of view. So runner application is already running. Git push to GitHub to trigger the event. Then you will see the workflow starts and some child process starts also worker.exe. Finally, sheet connection is established. At the end of the workflow, worker.exe and child process is terminated. And workflow.exe is sheet process. It is started by early bird injection and PPID spoofing from runner application. We implemented some injection technique in JavaScript. So far, I have talked about JavaScript version. Next, I will describe JavaScript version. We have discovered attack techniques that exploits Node.js extension. Node.js has extension called C++ add-on. This one can be used for attack. We call this technique malicious JavaScript custom action. There's a package called memory.js. This is not for the hacking, it is a legitimate package, but for hacker like us, there are useful functions available like open process and inject DLL. So we use this library in our POC. Also here is the actual POC code we developed. The workflow calls custom action. This custom action includes simple DLL and node module for the attack. Index.js is implemented in JavaScript and is designed to perform DLL injection using memory.js function. Open process and inject DLL are already implemented in memory.js, so JavaScript code is very simple. We use memory.js in this research, but we can implement on C++ add-on for arbitrary attacks. So unfortunately, there will be no demonstration today, but maybe talk to me later and I'll show you the demo. So as my final part, I talk about some considerations. First, let's discuss the attack scenario. Malicious action disguised as legitimate action could be published in the marketplace by attacker. Then users may mistakenly use the malicious action thinking it is a legitimate action. All users of GitHub Actions are potential victims, so this is a very big threat. Composite action makes this threat as realistic. Without composite action, step 1 is required, but who set up this? Even if users accidentally use the fake action, but they will not accidentally set step 1. So aggregating steps in a composite action is very important for the attacker. It can also expand the attack possibilities in advanced techniques. Run application tracks launch child process and kills all child process when the workflow is finished. And this means that the process launched for the attack will also be killed. It is tracked by process environment variable called runner tracking ID. So we can disable tracking by rewriting this variable like this. This makes the process persistent. By the way, process launched from the runner application have characteristic variable, so perhaps they can be used for detection. Next, let's consider how to protect it. GitHub recognizes these attacks as threat and publish best practice. Basically, it says that it is important to audit the code and the creators. Of course, it can be detected by security solutions like EDR or antivirus. A malicious JavaScript composite action is detected by EDR for defense evasion via masquerading. This is an unchangeable part of this technique, so it is a good detection point. Also, JS file is sometimes detected by antivirus. However, this is not effective because it can be easily bypassed. Like this slide, with a few changes, it is easy to bypass of detection, so antivirus is not an effective measure. Detecting malicious JavaScript custom action is a bit more difficult because this technique does not require to replace the script engine, so there is one less detection point. We think it is important to detect the attack behavior being carried out, not this technique itself. And this technique may also be effective against AMSI. From our quick analysis, it appears that Node.exe does not support AMSI.
So in my part, let me introduce GitHub Actions C2. GitHub Actions C2 is implemented by utilizing GitHub Actions run application as agent, she's agent. This is an abstract image of GitHub Actions C2. The runner application runs on target machine connecting to the GitHub, especially attacker's own repository. This connection becomes C2. To operate this attack, attacker pushes a malicious configuration file outside GitHub. This GitHub has two features. Firstly, the source process is a legitimate application, runner.wagner.exe. And the second point is that the destination is legitimate domain and IP. So how to establish C2? So as officially stated, runner application when launched performs a long polling against GitHub to await jobs. To manage runner as a C2 agent, assigning a unique label is needed. This allows attackers to send command individually when establish C2 connections with multiple targets. Without trouble, attacker ends up sending same commands to all connecting hosts. How to send a command? Initial commands can be executed via GitHub Actions workflow. Workflow jobs are described in configuration file on attacker's repository. We can trigger workflow by GitHub Actions like push. And in this case, we use a webhook event called repository dispatch. We can call this event using a curl, while passing instruction from outside GitHub. Plus, using just introduce malicious custom actions, more advanced attack can also be performed. I will show you a short demo to make it easier to imagine. Victim runs an application, and the attacker sends a command to run the calculation.exe. And the victim machine calculation.exe was launched, and after that, you can see also the PMI result on the attacker side. Attack scenario. So attack scenario is almost the same as the other C2. So firstly, attacker create a public repository for attacks. And then attacker send their run application to target using techniques such as phishing. After that, the target user unknowingly runs it as shown in the demo. About detections. So since source process and destination domain is legitimate, C2 establishment is hard to detect. So it's a very ordinary way, but don't miss a lot for activities related to GitHub Actions, C2, and just because they seem to be legitimate. Last part is other threat related to GitHub Actions. I will briefly introduce 3 threads. Firstly, freejacking. Freejacking is a process of using free cloud resources to perform crypto mining operations. Attacker execute mining script using GitHub resources, and after that, the attacker can get the reward. To utilize GitHub resources, the attacker sends pull requests have mining code to run other repositories. More precisely, forking a public repository and embedding mining code into GitHub Actions and sending pull requests trigger mining using GitHub resources. But to prevent this, GitHub changed the specification, and approval have been required to run workflow from public folks since April 2021. So attackers have shifted their focus toward automatically creating GitHub account, executing GitHub actions, and exploiting their resources. Secondly, malicious public fork and pull request. The idea is that if a self-hosted runner is being used with a public repository, GitHub Action may become a potential entry point for external attacker to gain initial foothold. This may allow attacker execute their code on the target machine. So GitHub is aware of this threat and recommended that using self-hosted runner only for private repository. However, it's worth noting that there are numerous organizations still utilize their hosted runner in public repository. So there are tools available for exploring public repository for that use self-hosted runner, and investigation are planned to access the actual situation. Lastly, steering secret. So GitHub provides a feature to create encrypted environment variable called secret as organization or repository level. So secret can be accessed by GitHub Actions when they are set up for the repository. So this poses a potential risk secret being stolen if attacker can access the secret through the GitHub Actions. So I ended up here conclusion that there are 3 points. Firstly, by utilizing the feature offered by CICD, so such as command and script execution, it's possible to launch attack within the legitimate CICD process. And second is that malicious code may infiltrate the pipeline without notice through a publicly available malicious plugin. We introduced this as a malicious custom action. And the last point is that there's a risk of enabling C2 through the legitimate feature offered by CICD, which are the user-owned host for executing tasks. So for future work, we are starting focusing on other CICD platform. So thank you for security, GitHub Actions security team for cooperation, and also thank you for Cloud Village team for accepting our talk. Thank you. Yeah. Yeah. And do you have any questions?
Yeah. Do you want to do questions out back or up front?
Okay.
Do you want to do them here or out there?
Try to hear.
Here?
Yeah. Okay. But if
I'll help bring it.
thank you.
So, is the same? Is it just as or just as easy if you're not using Windows as the target, or is it more difficult?
Target on Windows.
Yeah. So I saw a lot of target on Windows there.
Yeah.
Does Linux share the same vulnerabilities, or is it safer by default because it's not Windows and JScript?
So sorry. So could you say that again? Yeah.
Is the same attack vector as viable in a non-Windows environment?
Yeah. Yeah.
JScript only.
So about for JScript.
Well, because JScript isn't going to be anywhere.
JScript only. Yeah.
Right.
Yes.
Right.
And that also as for GitHub Actions as C2, so there's a hosted runner for Linux, so that it works. Okay.
Right.
Yeah. Thank you.
Thank you.